this and following few lectures, we will be studying the behavior of the solutions of a homogeneous LTI system from the point of view of the eigenvalue locations of the A matrix, okay, the system matrix. This analysis will be later very useful when we study eventually the concept of stability. Now, our object of inquiry is for the continuous time homogeneous LTI system. X equals X by homogeneous simply mean that we don't have any input parameters. This differential equation and the initial condition is denoted by X naught. And we're talking about a system of dimension n. Now, we have figured out that the solution of this system, starting from this initial condition, can be written as x of t equals e to the at, okay, state transition matrix, times the initial condition vector, x0, my initial state. Where since we are in continuous time, t is a real number. It starts from 0 and it goes to the right on the real line. For the discrete time case, well, before that, e to the at is the transition matrix, as we said, and remember how we constructed it or how it's defined. E to the at equals matrix plus ta plus t squared over 2 a squared plus t cube 3 factorial a cube plus so on. Is the series definition or construction of state transition matrix. It can also be computed by Laplace transform. In other words, we have e to the at equals inverse Laplace transform of this matrix Si minus A inverse. Okay. This is from our previous lectures. For the discrete time case, we can write analogously following discrete time homogeneous LTI system. We have x plus equals x, remember our x plus notation. It simply means that value of the state at the next time instant equals a times the value of the state at the present time. Sometimes it's written as x of k plus 1 or t plus 1 equals a times x of t. Now, the solution is much easier to write because the state transition matrix, we already almost have the state transition matrix. Namely, solution x of t equals a raised to the power t times the initial condition. Okay. As before, we have x0 denoting the initial state vector. The difference between this case and this case is that since now we're in discrete time, this time t can take only integer values. Okay, t in 0, 1, 2, and so on. Okay, now for this case, that is for the homogeneous LTI system case, we will be studying the relation between the possible behaviors of the solution and the eigenvalue locations of the A matrix. Okay, here and here. And for our study, we will make heavy use of the Jordan form representation of the A matrix. Before we start our analysis, let's talk about the behaviors that we will be interested in. So the possible behaviors of interest are as follows. Okay, so let's visit possible behaviors through some simple examples, and then we're going to generalize our observations. So by behaviors of interest of the solution, we mean the following. We will be studying the convergence behavior of the solution. And also we'll be interested in whether the solutions are bounded or unbounded. Okay, so unboundedness, and finally we will be talking about boundedness. Okay, all those three behaviors are closely related to one another. So let's start from behavior that we call, that's related to the convergence. So by convergence, we mean convergence to the origin or to the clue point, but without this alternative, we can always take the clue point to be the origin. Okay. So x of t going to zero, the solution converging to zero for all initial conditions. Okay. So that's what we mean by convergent behavior. All solutions converging to zero for all initial conditions. Now this, let's get the case from the continuous time point of view, so that it will be easier to find examples. Okay. So if this is the case for a continuous time system, if x of t is converging to zero for all possible initial conditions, it's only possible if this matrix e to the at state transition matrix is converging to zero itself. And by a matrix converging to zero, we mean simply all of its entries are converging to zero. So this implies, in fact, implied by, so this is equals relation, but let's not worry about that. If this is true, then each the at state transition matrix must converge to the zero matrix, okay, as t goes to infinity. Now, let's try to visualize this behavior through some real-life example. Okay, let's take mass spring system. Mass attached to a fixed frame with a linear spring, spring constant K, and this mass, suppose that we have friction in our system. Why? Let it denote the displacement of the block from the cooling position, and mass spring constant and damping coefficient or the friction coefficient are all positive. Okay. Now, we can easily write the model for the system. And y double dot, okay, y double dot is the acceleration, equals the total force acting on it. There are two forces. One of them is force due to spring, and the other is force due to friction. Force due to friction manifests itself through velocity, and force due to spring manifests itself through the displacement. So what we have is m y double dot equals minus dy dotted minus ky. Both are opposing forces. And then if we collect all the terms on the left side, we have simply ky equals 0. So this is the model of our system. Now let's put this presentation into state space. For this, what we do is we choose the state x1 as the displacement or position, and x2 as the velocity y. With that state choice, we immediately obtain x that equals a minus x. And what's A? For the first row, we look at the x1 dot equation. x1 that is y dot is x2, therefore that's the first row for A matrix. That's for the second row. x2 dot is y double dot is these guys thrown to the other side, and then we divide everything by n. In that case, what we have is minus k over n here and minus b over n for that entry. So that's our A matrix. Now, from real life experience, we know that because there is friction, the energy initially stored in the system will leak out of the system by as dissipation, as heat. Okay? It will go away from the system. So that means eventually the oscillations will become with smaller and smaller magnitude, and eventually the mass will reach a full stop. Okay. So in the model, it never really exactly reaches the full stop. It converges to zero, but nevertheless the behavior is there. Okay, so we can easily visualize that. Now, so that means that because this is true, this A matrix, no matter how you choose n, k, and b, provided they are all positive, should produce a state transition matrix that converges to zero. Okay, and that behavior, it turns out, has to do with the positions of the eigenvalues of the A matrix. So let's figure out the eigenvalues of this A matrix. Perhaps not exactly, but well, at least eigenvalues of A. Now A is a 2x2 matrix, so that means it will have two eigenvalues. Let's call them lambda 1 and lambda 2. What are eigenvalues? How do we compute them? They are the roots of the characteristic polynomial. That characteristic polynomial is the determinant of the matrix Si minus A. Eigenvalues of A are the roots of the determinant of matrix Si minus A. Now what's the determinant of Si minus A? Equals S squared plus 2b over n S plus k over n. Okay, so that's our characteristic polynomial. And since it's a second order polynomial, we can exactly write down the roots, but there's no need for our purpose. What we have here is a second order polynomial, and all the coefficients are positive. Being positive, okay? So that immediately gives us, or allows us to reach the conclusion that all the eigenvalues must necessarily, all the roots of this polynomial must necessarily be on the open left half plane. We're talking about the convex plane. In other words, this implies that the real parts of all eigenvalues, lambda 1 and lambda 2, are necessarily strictly less than 0 for all. Okay. So this is the case for this very simple example. Now, it turns out that this observation, or that condition, is both necessary and sufficient for the general case for e to the at converge to 0. In other words, if this is satisfied for a given homogeneous system, okay, I'm talking about the continuous time case, then all the solutions, okay, starting from all possible initial conditions, will converge to 0. Okay, so this is one of the results that we will eventually formalize. Necessary and sufficient for the AT to converge to 0. So well, we just discussed, therefore, through a simple example, what we mean by the behavior of convergence. Now let's talk about unbounded behavior. So what do we mean by that? we mean by an unbounded behavior for a homogeneous system is that a solution, okay, now we're not talking about all solutions, but if there exists a single solution such that its norm is diverging, its norm is going to infinity, then we call the behavior, okay, such behavior is an unbounded behavior for a system. In other words, if this is satisfied for at least one initial condition, x0, then the behavior, the associated behavior is called unbounded behavior. Okay? And eventually that will be very important when we talk about instability of linear systems. Okay. Now again, if this holds true, it must be that at least one of the entries of the e to the at state transition matrix must be blowing up. It must be going to infinity. And even if just a single entry of e to the at is diverging, then the norm of e to the at is diverging. In other words, this implies, and in fact is implied by this condition, that the norm of the state transition matrix is divergent. Now, let's, from a real example, obtain a case, a linear system, for which state transition matrix blows up. For that, let's begin with a nonlinear system and then linearize it. Okay, let's consider the pendulum. This is the direction of gravity. This is theta, this is the equilibrium position. And the normalized equation for the pendulum is theta double plus sine theta equals 0. Okay, we consider a friction-free case. This is normalized equation. Okay. Now let's linearize this system at the unstable equilibrium point. Okay. That is, it has two equilibrium points. One is theta equals 0, and theta dot equals 0. And there is theta equals pi, and theta dot equals 0. So if you linearize a system, the upright position, which we know from experience is unstable, linearization at theta equals pi. Let's choose the state as theta minus pi, and x2 as theta dot, okay, or x1 dot because pi is fixed. This choice yields the following linearization. Okay, at the upright equilibrium position, x dot equals 0, 1, 1, 0, x. Okay, this is now our A matrix. Okay, now the eigenvalues or the roots of the term of Si minus A is very easy to compute. It's the practice polynomial turns out to be s squared minus 1. It has two roots, one z plus 1, the other is z minus 1. Therefore, the eigenvalues are at 1 and 2 z minus 1. Okay. Now, that we have an eigenvalue that with the positive real part or on the right half plane is close related, for this example at least, to the behavior that the state transition matrix is divergent. So if one of the eigenvalues, and this can be generalized, if one of the eigenvalues is with positive real part, then e to the at, okay, has a diverging norm, and that will give us the unbounded behavior. Now, in the first example, the condition that, or the observation that we made turned out to be both a necessary and sufficient condition for e to the at to do what we expect from it to do. Okay? In this case, this observation is only sufficient for e to the at to diverge, or normally to diverge. Okay. We'll see later on why it's only sufficient and not necessary. Sufficient for e to the at to diverge. Okay. Now, before we move on to the boundedness behavior, let's stop and make an important remark. Okay. Now, let's talk over the example. For this example, it can be shown that e to the at, the normal e to the at, is unbounded. Okay, it diverges. And we know that x of t is e to the at times the initial condition vector. So this holds x of t equals e to the at times x0, and e to the at is such that its norm is exploited. Okay? It's divergent. Now, does that mean that for any initial condition, the solution, because this is satisfied, also blows up? The normal solution also blows up. Turns out that the answer is no, not necessarily. And it's easy to find a counterexample. Let's talk over this example. Remark. Not all solutions are unbounded. Okay? Just because e to the at is unbounded does not mean necessarily that all solutions are unbounded. Okay? It only means that some solutions are unbounded. And let's find a bounded solution despite the fact that e to the at is diverging. Okay? It's not difficult to see that. For instance, let's start our system from the initial condition x0 equals 1 minus 1. Then solution turns out to equal 1 minus 1 e to the minus t. That is, if you start your system from this initial condition, x of t not only remains bounded, but also it's converging to the 0, despite the fact that e to the at, the state transition matrix, is explored. And that has to do with the fact that this initial condition is not an arbitrary initial condition. It's indeed the eigenvector corresponding to the stable eigenvector. If you start at that very special initial condition, then the solution turns out to be converging to 0, despite this behavior. Okay, and finally, let's talk about the third behavior, is boundedness. Xt remain bounded for all initial conditions x0. And this implies, and is implied by the following condition: the norm of the state transition matrix, we should be able to find a constant such that the normal state transition matrix is never above that positive constant. Again, let's find an example. In fact, we can use pendulum once again this time. We'll linearize it here, the down right point. And we know that dynamic equilibrium point is stable for everyday experience. Minimization of pendulum at the other equilibrium point at x1 equals theta, x2 equals x1 dot or theta dot yields the following homogeneous system. 0, 1. This time we have minus 1 for this energy. Previously we had the other equilibrium point x. Let's figure out the eigenvalues of this A matrix. The characteristic polynomial is s squared plus 1. Therefore, we have two roots that both are purely imaginary. Lambda 1 equals j and lambda 2 equals minus j. We have a complex conjugate pair on the imaginary axis. Now, these are the eigenvalue locations of this A matrix or of that system. How about the norm of E to the AT? Okay, is it bounded? Well, from one of the previous lectures, we know that it's a skew-symmetric matrix, the A matrix. Therefore, E to the AT is an orthogonal matrix. And we know that orthogonal matrices are norm-preserving. So from that norm-preserving property, we can immediately write the norm of E to the AT. In fact, it's constant. Okay, and by norm, we need a norm. So we have a bounded state transition matrix, and we have eigenvalues on the imaginary axis. And the observation that we want to make at this point is that all our eigenvalues are with real parts that are either 0 or negative. In this case, real parts are exactly 0, but generalized or all values. And it turns out that this is closely related to the boundedness behavior of the state transition matrix, and from there eventually boundedness property of the solution itself. Now, is this sufficient condition for E to the AT to be bounded? It turns out that it isn't. We will see why shortly. This is only a necessary condition for state transition matrix to be bound, but it's not sufficient. And to have some idea why that's only necessary and not sufficient, let's consider the following example, again, from the mechanical world. Okay, our second remark regarding our behaviors in general. Condition that all the eigenvalues are on the closed left half plane is not sufficient for all solutions to remain bounded. Here is a very simple example. Take mass on a flat surface with no friction. We have no friction, we have no spring, we have no force whatsoever acting on our mass. Okay, again, let y indicate the displacement. The model of the system is and y dot, okay, this is correction, equals total force. Total force is 0, therefore my dot equals 0, therefore my double dot equals 0, therefore y double dot equals 0. So this yields, again, by state choice x1 equals y and x2 equals y dot, following a matrix 0, 1, 0, 0. Since it's in triangle form, we directly see that both eigenvalues are at 0. In other words, all eigenvalues satisfy this condition here. However, even though that condition is satisfied, we don't have boundedness of e to the h, okay, so the transition matrix, because we don't have boundedness of the solution, the very solution. What's the solution, by the way? 1 equals 0. What we have is y dot of t is constant. Since acceleration is 0, that means the velocity is constant. If the velocity is constant, so that means the position is increasing or decreasing linearly, but it's not. Whatever it's doing is not remaining constant. It's not remaining bounded. Okay. Y of t equals y of 0 plus initial velocity times t. Okay. Because this is constant and we have t is increasing, therefore if this is positive, then y of t is increasing. If this is negative, then y of t is decreasing. But in any case, it's not remaining. Okay. So these examples gave us some rough idea on the possible behaviors that we will eventually be studying in a more formal fashion. Okay. And now we can begin bearing the links between the eigenvalues of A and the behavior of the state transition matrix. Because it's a little bit easier, let's start from the discrete time case, even though all our examples were from continuous time. Okay. Now, to make the link apparent, link between the eigenvalue locations of A matrix and the behavior of the state transition matrix. Now, we will make use of the Jordan form representation of the A matrix. For that, we have to visit certain theorems from linear systems 501 course. So we know from 501 patterns. Every matrix can be put into so-called Jordan form, where we have lots of zeros in a very simple form to study. So let's remember what Jordan form was. For every matrix, for every square matrix, A, and it's allowed to be with complex entries, though we will only be interested in real case, but this is a more general theorem. There exists a non-singular change of basis matrix or change of coordinates matrix, let's call it P, which is of same size as A, that transforms A into so-called Jordan form, and Jordan form matrix is usually denoted by letter J into J, where J is, or the relation between J and A is, J equals PA, P inverse, and after that transformation, we have this nice block diagonal form. J1, 0, 0, 0, J2, 0. We have J now. Where each Ji is a so-called Jordan block of the form Ji equals, it's a triangular matrix. So it has all lambda i's on the main diagonal, and the sub-diagonal we have all ones, and the remaining entries are 0. So this is a square matrix Ni by Ni. Okay. If you sum all these Ni's, they must add up to N. Furthermore, where each lambda I is an eigenvalue of the original matrix A, and the number L, or the number of Jordan blocks, is the number of independent eigenvectors of A, equals the number of linearly independent eigenvectors. Each A has a unique up to every ordering blocks J. So each A has a unique J representation. With this remark kept in mind. Matrix J is called the Jordan normal form. Or simply the Jordan form. Okay, so this theorem that we borrowed from 541 will be very helpful in our analysis. There are a couple of remarks that I want to make. First, we do not assume lambda I not equals lambda J for I not equals J. For instance, A equals the identity matrix, so it's already in Jordan form. Then A is already with A equals I equals J, that equals J1, J2, Jn, with each Jordan block, Ji, being equal to this 1 by 1 block. In other words, a scalar which equals 1. 4, I equals 1, 2, n. Okay, now let's talk about the state transition matrix for the discrete time case from the point of view of the Jordan representation. Okay. Now we're interested in the behavior of the state transition matrix, which is A to the K for discrete time, as K or T as T goes to infinity. Okay. So let's ask this question, which is directly related to the behavior of the solutions for a discrete time system. What happens to A to the K, the powers of K, or the state transition matrix for discrete time, as K goes to infinity, where K's are discrete time, 0, 1, 2, and so on. Okay. Now, one nice thing about this powers is that they can be easily represented by the powers of the Jordan form. So we know that J equals P A P inverse. Okay. So that means A equals P inverse J P. Then A squared equals P inverse J P times P inverse J P. Now this P and this P inverse, they will cancel one another. They make identity, so we can just remove them. But we have this P inverse J, another J, times P. J, another J makes J squared. So what we have here is P inverse J squared P. If you consider A cubed, then you have this times this, and then another this guy. We have PP inverse here, and then PP inverse here, and all those PP inverses will cancel, and you will have J multiplying another J and multiplying another J, and so on. So what we have is, for any power, AK can be written as P inverse J raised to the power of K, J being the Jordan form of A, times P. And since the Jordan form has a very special form, okay, it's block diagonal, it can be written as P inverse times P. J1 is the first block. The first block of J to the K is J1 to the K because of the block diagonal form. And so J2 to the K and JL. Now, what remains is to figure out the form of an individual Jordan block raised to an arbitrary power. Okay, so we're going to ask now, we're going to try to answer the following question. What's Ji raised to the power? Okay. Now, by induction, we can write the following. Ji to the the k. If Ji, the ith Jordan block, is a 1 by 1 block, in other words, if it's a scalar, then its kth power is simply that scalar raised to the kth power. There's nothing interesting or difficult about that. So that's that. How about Ji to the k for the 2 by 2 block? Okay. So we're talking about this 0 lambda. This is a 2 by 2 Jordan block. Okay. So that equals lambda I k lambda I k minus 1 0 lambda I to the k. Okay, it's not that difficult to show. And as for Ji to the k 3 by 3 block, so we're talking about now this lambda I 1 0 0 lambda I 1 0 0 lambda I. Okay, we're talking about this matrix. That equals this one lambda I k lambda I k minus 1 0 lambda I k lambda I k minus 1 0 0 lambda I k. And for this entry we have, turns out, k times k minus 1 lambda I k minus 2 divided by 2 factorial. Okay. For the general expression, which can be guessed from the first 3 instances, see text. Okay, see the text. Okay, this is the textbook. Okay. Anyway, just these 3 instances are enough to give us the idea to make the necessary deductions about eigenvalue locations of A matrix and the behavior of A raised to the power k. In other words, the behavior of the state transition matrix for the discrete time homogeneous case. Okay, hence we deduce, which will be, these conclusions will be very important when we study stability. Okay. 1. Suppose that the magnitude of the eigenvalue lambda I is strictly less than 1. And it's true, suppose, for all eigenvalues of A. Then Ji raised to the power k is 1. Okay. Now we have this form, and what we have is all these lambda i's, they are with strictly smaller than 1 magnitude. Okay. So that means as k increases, they're converging to 0, and they're converging to 0 exponentially. Now, even though we have k terms here and there, here we have k squared term, and those polynomial terms, they tend to increase as k goes to infinity, but the exponential decrease will dominate polynomial increase, and even though we have those polynomials, all the terms will converge to 0 if all the eigenvalues are with strictly less than 1 magnitudes. And if all the Jordan blocks converge to 0, so that means J to the k, the kth power of the Jordan form converges to 0, and if the Jordan form converges to 0, then A to the k must also converge to 0. Then Ji converges to 0 as k goes to infinity for all indices. Then J to the k converges to 0. J is the Jordan matrix. That means A to the k converges to 0. Okay, because A to the k is simply subconstant matrix times jk. times some other constant matrix. Hence, it goes a to the k equals inverse jk p. Therefore, for convergence behavior, for discrete time system, this condition would imply, would give us what we want. This is the convergence behavior. Okay. It turns out that this is satisfied, then this must hold true. Therefore, that's a both-way implication. So it's a necessary sufficient condition for convergence behavior that the old eigenvalues are strictly less than 1 magnitudes. Let's look at the bound of this behavior. Suppose lambda I magnitude is not larger than 1 for all I. Okay. And size of the Jordan block J, let's call index n, Jn is 1 by 1 whenever the magnitude of the corresponding eigenvalue is exactly 1. Then all the Jordan blocks remain bounded. Is one can find constant such that norms of the kth power of each Jordan block is strictly less than that constant C for all k. Then, due to that, a to the k is the transition matrix remains bounded. Okay, so let's reread this. If magnitudes are no larger than 1, okay, there are two possibilities. One is magnitude is strictly less than 1. If magnitude is strictly less than 1, then that corresponding Jordan block will go to, will converge to 0. If, however, the magnitude equals exactly 1, then this thing is not converging to 0. Okay, lambda I raised to the power k. Because the magnitude of lambda I to the k is also 1, therefore it's bounded, it's not converging to 0. And since it's not converging to 0 exponentially, it will not be able to dominate or repress the polynomial increase of these terms, k term, k squared term, and higher terms for higher order Jordan blocks. Okay? There's only one situation where we don't have this polynomial term, and it's here, for the 1 by 1 case. So therefore, whenever magnitude equals exactly 1, then the corresponding block must be 1 by 1 if you want boundedness. And then if those conditions are satisfied, the state transition matrix A to K remains bounded. And finally, for the remaining case, suppose there exists some index such that either the magnitude of the corresponding eigenvalue is strictly larger than 1, or it equals 1, magnitude equals 1, but the corresponding Jordan block's size is 2 by 2 or larger. In other words, we have those polynomial terms, then we will have some unbounded terms which will manifest themselves as the unboundedness of T-state transition vectors. Lambda I equals 1, and the size of the corresponding Jordan plot is 2 by 2 or larger. And K is unbounded. Okay, which in turn results in the unboundedness behavior of T.